The slide for you.
Okay, for sure, yeah.
Okay.
Hi everyone, thanks so much for coming today. My name is Savitha, I'm a software engineer at Coinbase. So today I'll be giving a short presentation on distributed consensus in blockchain. Next.
Oh, sorry. There we go.
Okay, so basically what is distributed consensus? So most of the applications that we deal with are client-server based models. So what is a distributed system? A distributed system is one which is in essential to explain the term using the word itself, distributed across multiple nodes or multiple entities. So basically in such a system, how do you achieve reliability and consensus? So that is basically the question of what is distributed consensus. So in a distributed system, since there is a lack of a central authority, there is no one person that you can trust. For instance, say there's a banking application, I trust my bank to make sure that I'm not double spending or the money that I am receiving is not being double spent. But in a distributed system with the lack of a central authority, we do not know which node is going to be potentially malicious. So each and every node is treated with the same view that it could be a malicious node. So in that system, how do you achieve consensus? So that is the fundamental problem of distributed consensus. Next. So let's say, for instance, the node here wants to propagate the value of x equal to 5 to all the nodes in the system. So basically, this is, think of it as a general distributed system. So there are nodes which are connected. So it propagates the value to all the nodes that it is connected to. And all the nodes send back an acknowledgement saying that, okay, cool, we can update the value that we have to that value that you told us to do. So once this node receives an ACK or an acknowledgement from all the nodes that it broadcast a value to, it understands that, okay, all the nodes are going to have that copy. So it can also go ahead and make sure that the entire network is in consensus. So this is basically in a normal distributed system how consensus is reached. So this is pretty much straightforward. Next slide, please. Okay, so till now it was fine. You just send an acknowledgement, you get it back, you reach consensus. But let's complicate things a little, shall we? So let's say what if there were malicious actors in the system. So when I send across a value, I may not get that value back, or I may get a tampered value back, right? So I don't know which of the actors or the nodes in the system are potentially malicious. So how do you deal with this problem? Next. So this brings us to one of the classic problems in computer science called the Byzantine generals problem. So the Byzantine is basically, I think, the Eastern Roman Empire or army. So basically it's a theoretical problem which says, okay, there's an enemy and there are several divisions of the Byzantine army which are circling or surrounding the enemy. But none of those generals or the divisions of the army can talk directly to each other. But still they need to reach some sort of a consensus on what time or how to attack the enemy. So the generals or the different divisions need to talk to each other, but they cannot do so directly. They need to do it in terms of having some messenger. So to complicate things further, it could also happen that the general could be, one or more generals could be a traitor. So you don't know. So if, say, one of the generals issues a command to attack the enemy, the other general could just change the attack to retreat and kind of just mess things around. So let's say for in this case scenario, what happens is general 2 over here is issuing one attack command and one retreat command. So you can see that general 3 is just confused. He's just getting one attack and one retreat. So he doesn't know what to do. So in this system, there is no mutual agreement on whether they should attack or whether they should retreat, because general 3 does not know what is to be done. Next. So this brings us, so how does that relate to computer science? So this was a theoretical formulation of a problem, but how does that correlate back to distributed systems? That's what we're interested in. So let's think of Byzantine generals as a one-to-one mapping between the generals and the nodes. So the nodes are potentially like the generals, and like a traitor, you can have a node which has some sort of a malicious intent. So, like I said, some could be honest and the others are not. So this is one of the, again, classic problems in computer science, which is kind of hard to solve. But people have come up with ways to do it. So in blockchain, again, to reiterate on the fact that it's decentralized, there is no single source of truth, or no node can be trusted in entirety to make sure that it is not acting against the interests of the network. So one of the algorithms to solve the Byzantine generals problem is the practical Byzantine fault tolerance algorithm, PBFT for short. So basically what it says is that consensus can be received if at most 1/3 of the nodes in the system are traitors. So that means 2/3 majority is needed to actually go ahead and reach consensus. So it follows like a client leader kind of a model. So one node propagates information to the other client nodes, and the client nodes once they receive that value, they either decide, depending on whether they are traitors or whether they're honest actors in the system, they send back a response to the leader. So the leader awaits for f+1 replies, so where f happens to be the maximum number of traitor generals. So we can see that at most 1/3 of the people or the nodes in that system can be malicious. So with this, we have kind of solved the problem of having malicious people. Not exactly, but to some extent, we're able to tolerate like 1/3 of the system being acting against the wishes of the network. So, okay, so yeah, next. So that is done. So let's add further complications. So what happens if like one entity controls the system? So we had malicious actors, now we have one entity which is trying to take over the system. So in that case, like, how do you solve this problem? So this brings us to like the next concept that I'm going to be talking about. So the next concept that I'm going to be talking about is called the Sybil attack. So Sybil attack is an attack is formally defined as an attack where one entity tries to gain majority in the system. So this could be as simple as one entity trying to create multiple Facebook profiles to perhaps spread fake news, or one entity trying to create multiple Amazon profiles to promote their product, create multiple customer profiles to write fake reviews about a product. It could be anything. So from as simple as fake news and fake reviews of products on Amazon. So basically the intention of that one actor is to have multiple identities in the network and use that to his or her advantage. So obviously this is not something that we want. We want a democracy. We want people to be, we want to preferably have a one-to-one mapping between the identity and the actual actor who is behind that identity. So, and like I said, Sybil attacks are very, very hard to detect and prevent, because in the network, you will just see identities, right? You'll just see like a Facebook profile, or you'll see like an Amazon profile. Like, it's kind of like, think about it, it's really hard to detect who is behind those profiles, right? So like in a centralized system, maybe like, Amazon could do something like IP whitelisting. It could just say that, from this IP only so many profiles can be created, or something like that. So, or it could have, multiple layers of authentication to create an identity, so that it's not very cheap to create an identity. So these are like some of the ways how you combat Sybil attacks in a general client-server model. But again, going back to our topic of interest today, in a distributed system, again, how will you do IP whitelisting? Like, who will enforce two-factor authentication? So this is not a straightforward straightforward solution in the case of blockchain or the distributed systems. So again, this is just a sample of Sybil attack where one node is actually having multiple identities, but in the external world, it appears that all the nodes are just one single entities, but it's actually being controlled by one person. Okay, so there are two widely used algorithms to find consensus and basically to combat Sybil attacks. So one is called the proof of work and one is called proof of stake. So we'll be actually delving into both of these in detail. Okay, so what is proof of work? So basically proof of work is a piece of data which is costly to produce but very cheap to verify. So what do I mean by that? So let's take an example. Let's say the piece of data is ABCDE, And let's say I use a nonce. So a nonce is basically a 32-bit field that is added onto a piece of data. So a property of a hash function in computer science is that when you have a varying length input, when you take a hash of it, the output is of a fixed size. So you can, so that is basically what a hash function in computer science does, like the standard hashing algorithms like SHA-256. So let's say I have a piece of data and I want to add a nonce to it. So nonce is basically just a field. So once I take a hash of that data and nonce, I will impose a condition on the system that whoever is trying to find that nonce, that he should find a nonce such that it begins with, say, 8 zeros in the beginning. So let's see how difficult or easy this is, because what is the property of a good hash function? It's that suppose you change the input slightly, even if you perturb the input even by a little bit, the output is completely different from what the original input was, right? So if I have, if say the original nonce was 1 and I got the hash to be some A, B, C, D, E, and if I add the nonce to 2, it won't be A, B, C, D, F or something like that. It will be completely different, like Z, D, X, Y, Z or something like that. So that is the property of a good hash function. So now you can see that the only way for anybody to find that nonce is to brute force all possible nonces. So there is actually no way for any person who's trying to solve this problem, who's trying to solve that equation where nonce is the unknown, to find it by just a random or a lucky guess. So it's not happening. The probability is like perhaps too low. So once that person claims that he found the nonce, it's very easy for the others in the system to verify, because all they have to do is hash whatever the data and the nonce is. The data is constant for everybody. Only the nonce is something that people are trying to find. So once you know that, this verification is this is done in O of one time. Like you can just take a hash of the given data and the nonce. But to find this, you're actually spending CPU cycles, you're actually spending energy, you're actually spending computational resources to run through all possible combinations and all possible values to get that, get the hash value which meets a certain set of requirements. So if I want to make it harder, I'll probably add another 0. So that will increase the difficulty, because I'm not going to easily get a hash which begins with 10 zeros or something like that. The more number of zeros, the more number of conditions that I add onto this problem, the harder it is going to be. Okay, so how does this relate to blockchain? So what we spoke in general was, in general, what is proof of work, but how does this relate to what is happening in blockchains today? So we spoke about their sample data. So in actual blockchain, the total data that is actually hashed is the hash of the previous block plus the current block and the nonce, which needs to be found by the so-called miners. So miners are basically the people who are trying to, add a block onto the blockchain. So a block has a set of transactions, and they are the ones who are claiming rights to go and add that block onto the blockchain. So since I already explained, the only way for people to find this nonce is to actually spend resources, is to actually spend energy. So what is the incentive for these people to go ahead and do that? So unless there is something in it for them, they're not going to spend all those resources. It's very expensive to buy mining equipment and that kind of computing resources, right? So what is the reward for them? So for them, if they successfully find the nonce, they get a block reward, which is basically Bitcoin. Currently, I think it's about 12.5 Bitcoin per block, and they get transaction fees associated with the transactions in that block. So that is what incentivizes it. So there is incentive for the person who's doing the validation to do a good job, because he is getting paid in the currency. If he does any malicious activity or intent, the value of the currency will obviously go down. So the whatever value he has is going to go down, and he will never get a chance to be a validator again. So once he's been identified as a malicious user, he's never going to be chosen again. The value of the currency that he has is obviously going to go down. It does not work. If you think about, if his intention is to be in the competitive spirit and make money, it does not go ahead with it. So that is basically how proof of stake works, to ensure that a single identity is not getting the same chance all the time. So we saw that in proof of work, it was an exponential curve because of the mining equipment and the resources. But here, it's a simple correlation. If I am willing to stake 10x more coins, I have 10 times the higher chance, because all the equations that we saw were a simple multiplication of the units, number of units of currency times some factor, right? So if I'm willing to stake more currency, I'm obviously getting a higher chance. So there are different schools of thought which argue which is more favorable. Like, I don't have a strong opinion here, but some people say this is more fair. Some people say that the other one is more fair, so it's just, debatable. So this is basically the conclusion of the two consensus algorithms that are used in blockchains today. So if you have any questions, I'd be happy to take them.
Do you guys have to run like full nodes and all that? Like, so you have to, and do you typically write your own clients, or do you just use, because the other question is like, how do you keep up to date with, like 20 different cryptocurrencies as they change?
So I'm not like too familiar with the workings of the team, because I don't work with that team directly. So, but I'll try to answer your question in the best way as possible. So the way they have designed the systems, to the best of my knowledge, again, I may not be 100% correct here, is that they try to use, so they have like a general wallet which can talk to multiple blockchains. So adding a new asset will be as simple as adding a new implementation of that wallet. So that wallet can be a BTC wallet, it could be an XRP wallet, it could be an Ethereum wallet or anything like that. So they have tried to make the architecture scalable such that adding more assets will be easier.
What are your thoughts on like the different ways to generate randomness on chain? Like how like Affinity does it compared to like how Ethereum is trying to do it. Any strong thoughts one way or the other?
Actually, no, I'm not like very opinionated on how these people are doing it, but
okay.
Yeah. Do you have any? Like, I'd be happy to discuss.
Okay.
Do you code and go?
No, but some of the teams do at my company.
Do you have any strong feelings about proof of stake? Just in general, I mean, it's untested.
Yeah.
It's all very nuanced technology.
Right.
But just like, do you think it's a more elegant solution? Do you just like?
I like the solution, but like you said, I don't know the security loopholes yet.
Right.
So on paper, it looks pretty good to me. It looks like it's going to work. It looks like there is enough incentive, but I also see two main problems with it, in the sense that how long will transaction fees be sustainable or high enough for people to continue in the game. So that's one of the problems that I see with it. But overall, I think it's a good solution, because Bitcoin has been accused of, being very energy intensive.
I thought there was some proof of stake implementation, like Decreed, and what else?
Yeah. Ethereum also was planning to move to.
Yeah, but I think that Decreed is already.
Isn't that delegated proof of stake though?
I'm not sure.
I think it's delegated proof of stake, the one with the voters, right?
Yeah.
Could you explain it a little more? I don't know how that's specific.
Okay, like I'm not like too familiar, but I'll try to explain from my understanding. So here, what you do is you choose a validator based on the age of the coin and how many units of currency is willing to put at stake. In delegated proof of stake, there's a voting mechanism. So basically, a few validators try to volunteer, saying that they want to be the validators, because again, the incentive for them is the transaction fees as reward. So basically, it happens as a voting system. So the person who has more currency has probably a better say in the vote. Suppose he needn't be the one with the most currency. He could be backed by a guy who has a lot of currency, so his vote may take more value. So the implementations could differ, but basically the idea is that you choose a validator based on some sort of a voting mechanism. It's not just based on how much currency he has in the to offer for stake.
To kind of add to that, another way that's kind of easier to think about, like think about governance. You are delegating your vote to someone that probably knows the issues better, but then you get into trade-offs regarding like security, like centralization. So there's it's complicated.
All right, I'll have no more questions, and one last round of applause for Savitha. And we have the room for about another 20 minutes. You're welcome to hang out. Please take some pastries, bread, walk out with a whole box or a whole bag, please, and give them out. Thank you so much.
These people to continue staying in the game and be competitive in nature. So what are the disadvantages? Like I already mentioned, it's very energy intensive and it's very expensive because you need to actually buy these equipment. It's not like having one computer or so. It's probably like a server farm or something like that. Excuse me. Next. Okay, let's take example of how a blockchain looks today. So you have, like I mentioned, all the blocks are connected to the previous hashes of the previous block. So this is basically how a blockchain looks. So let's say an actor is trying to act in malicious intent. So can you change? So let's say there's an actor who wants to change the value in this block. Let's say he spent some Bitcoin in that block, but he wants to change it to something and say he didn't do it. So probably he wants to like double spend that money. But you know the property of a hash function. If you change the input, the entire block's hash value will change. So once you change that block's hash value, this reference is no longer valid because it's not pointing to the right previous block, right? So this entire chain from here has to be recomputed. But in that time, another block is getting added because people are continuing to transact in Bitcoin. So basically, before a new block gets added, he needs to compute the hashes of each and every block. So you can see that the further he goes behind from the latest block, the harder it is going to get because each block he has to go through that intensive process of finding the nonce and confirming with the network that whatever his so-called malicious intent was actually okay. So this is basically about proof of work, and like, do you want to ask if there's any questions? I can take it now.
Have you ever run into a situation where there's been like 2 or 3 nodes or a good amount of nodes that have been compromised to where it's something to where it's just that much more extensive as far as like trying to figure out what the correct hash is, or that never really happens? It's like it's mostly like 70% of the nodes are always in a solid state.
Mostly it is in a solid state, but the thing is, it could, if is the intent that you're talking about malicious intent or an honest intent? Like, in what intent are you telling that?
Well, for me, it seems that the only way to compromise something like this is to go for the nodes.
Right.
Like, it doesn't even make sense to do anything with the hashes.
Yeah, so if I have to change the information in that block, I need to, the entire hash of the block changes, right? So my block basically has transactions. So my block has the value that Savitha, sent you some Bitcoin. So that's how basically you record each and every transaction that happens on the block, on the Bitcoin network. So if I want to change the value and say that I didn't send any Bitcoin to you, I'm just changing the value, right? So if I change the value, the hash that was computed for the block, because we saw earlier that what was the data? The data was hash of the previous block plus the transactions plus a nonce which was computed. So when you change that transaction value, the hash changes, right? Mm-hmm. So when you change the hash of the block, that becomes invalid because the next block has lost the reference to the previous block. It's not a valid reference anymore.
It hasn't happened with the Bitcoin blockchain, but other blockchains that had fewer nodes have had 51% attacks against them.
Yeah.
Most recently, yeah, and it's because
Bitcoin
there aren't that many nodes. The network isn't big enough, and so for a malicious actor to come in and take over the nodes and start changing this is possible.
That Coinbase in any way?
Sorry?
The BTC 51% attack? Did
Sorry?
that affect Coinbase in any way?
No, not that I know of.
So as a chain is being created, nodes verify and compute basically accept a block. How do you find out how many nodes actually accepted that block? Like where is that recorded at?
As in, can you come again?
Okay, so theoretically you would say, okay, if 6 nodes accepted this block, I could assume that the transaction is legitimate, or the block is legitimate. Where is that stored at? Is the number of
Confirmations.
yeah,
Yeah.
is that stored in the blockchain itself, or is that?
It'll
Like-
show, and if you use a blockchain explorer, it'll tell you continually how many confirmations are happening.
Yeah.
Yeah, the number of
Like you-
confirmations is depth, it's not parallel.
Oh, it's not number of nodes?
Attestations. No, actually, the way it works is you validate the block yourself, and if it's valid, you
Yeah.
accept it. You don't need to
Yeah.
hear from other nodes that it's valid. If other nodes prefer a different chain, that chain will
Fork.
become longer, and then you'll hear that there's a longer chain, and you'll switch.
Yeah.
And that happens.
Yeah, that's a fork that happens. So basically, you don't need validations because you are the one who's doing the validation, and it's on you to do it correctly, right? So that's the onus. It's always even when we come to proof of stake as well. So basically, it's on the validator or on the miner to make sure that things are fine. Because think about it, he's incentivized to do it because he's getting back the Bitcoin in reward. So if he does a shoddy job at it, like obviously the value of the currency is going to devaluate, right? So whatever he's getting as block reward is the value of that currency is going to go down. So if something happens like that, so he's incentivized if you think about it from the economics perspective of it, unless he has the intention of taking a financial loss or something, if he wants to continually be in a capitalistic market where it's competitive and he wants to make money, there is no incentive for him to, do that mistake.
Yeah, I think one thing about it is just verification or confirmation. So even if you verify the block, you're not sure if you're on a fork or if you're on the main one yet.
Yeah.
So it's like that. I guess that's the question I have. Is like, I'm assuming that you look at the number of blocks that have been verified past that one.
Yeah, so if there's a fork, then you go back to the point where the fork was. So basically how it happens is you will not probably have the latest state of the blockchain with you, right? So when you take the latest state of the block, you go back to the lowest common ancestor and see that there has been another fork on the blockchain. So then you know that it has forked and it's probably time for you to update whatever information you have. It could so happen that you're continuing and it has forked on another chain and you don't know about it. Okay, so let's do a simple analysis of reward potential and the investment. So in proof of work, it is exponential because let's say if I'm willing to invest some X amount of dollars, I can buy a certain set of mining equipment. But as we know, when you purchase hardware in bulk, it is much cheaper. So if I'm willing to invest more amount of money or fiat currency to buy mining equipment, I can get exponentially higher power of computing resources, and also hardware prices keep decreasing. So like today, for the same money, I was able to get some computing resources. 6 months down the line, I'll probably be able to get much more. So the reward potential is exponential in the sense that the more you invest, there's a very, very high chance that you will actually gain reward, the block reward and the transaction fees. Okay, so we decided that yes, this would achieve consensus in the distributed system, but we also spoke about how it is very intensive, energy intensive. So basically you need mining farms, you need cooling equipment, you need basically a lot of physical resources and energy to keep this sustainable and running. So is there a way to do the same thing? Is there a way to achieve consensus without actually, taking a toll on the environment? So that's the next question we'll try to answer. So there's another algorithm that was actually developed. I think this was developed by some Reddit user, or somebody posted this on Reddit. It was like much later after the original proof of work algorithm. This algorithm is called proof of stake. So basically, what is stake? Stake is something that you deposit as collateral. Think of something like you put in an escrow account or something. So you're willing to stake that much of currency or that value into the system. So why do you do that? Because you want to be the validator. So that's how you when you put up that much of money of stake, you're saying that, yes, I'm willing to stake this much of currency and I'm willing to do the right job. So the reward in this case, so like I said, what is, in any case, whether it's the miner or the person who's staking, who in this case he's called a forger or a validator, he needs to be incentivized to stay in the system and keep it going, right? Like if there is no incentive or reward, like why should I stake all my currencies? So the reward here is that when you do a transaction, there is transaction fees, but there is no new currency that is minted in the process. So the advantage is that it is very energy intensive, and Stellar, then Black Coin, Pure Coin, all these things actually use proof of stake. So we'll delve into how this actually works. Okay, let's say there are two actors or two users. Say, let's say Alice is willing to put up 100 units of the currency at stake, and let's say Bob is willing to put up 10 units of the currency at stake. So since Alice is trying to put more units of currency, Alice has more skin in the game. She has more to stake. So she has a higher chance of being selected to be the validator. So a validator is basically the one who gets the right to actually confirm the block and add it to the chain. So, but if you think about it, it looks like the person who always has the most money gets a higher chance. So that's again unfair, right? So it could be that when the currency was started, those who were initially involved had a lot of that currency and they keep getting the chance again and again. So that's not exactly fair again on the entire system to keep it healthy and distributed. So so how do you prevent the wealthiest entity or a set of few entities from actually controlling, being the validator each and every time? So you need to make it distributed. This should not be a centralized system. So that's the ultimate goal, right? So there are two methods of finding a new validator. So what you try to do is you try to introduce some factor of randomness so that the same person or the same entity or the same address, I'm using all these terms kind of interchangeably. It's technically everything is an address. I'm just interchangeably using it so that it's easier to talk in terms of users and call them Alice and Bob, etc. So what you do is you add some sort of a random factor. So there are like two ways of finding a new validator. One is called the coin age based selection. So what do you do in the coin age based selection? So what you do is, suppose there's a user who's willing to stake say 10 units of the currency. You also factor in the age of the coin. So what is the age of the coin? So age of the coin is basically how long that coin has not been spent. So if the coin gets spent or if that coin gets recorded in the block, the age of the coin is reset to 1. So how long has that user held that coin? So that is called the coin age. So that you factor in as as one of the parameters to determine the age of the coin. So whoever has the highest age of the coin times the number of coins that they're willing to stake gets a chance to be chosen as the validator. So this is like one method. So the way we prevent the same guy is we set his coin age to 0. So the next time he doesn't get picked again. So he has to wait for a period of about 30 days before he's able to be chosen as the validator again. So in this, you're preventing the same wealthy guy from, getting a chance to be the validator and doing whatever he pleases to. So the other is called the randomized block selection. You take a block which has like the lowest hash value, or you introduce some sort of a random number. Basically, the idea here is that you do not let the guy with the most amount of money or the most amount of currency become the validator each and every time. You introduce some sort of like a randomness or some sort of perturbance such that that process becomes random and he does not get the chance all the time. So this is basically how proof of stake works. The one who is chosen as the validator gets the right to confirm the transactions. Again, the reward here is in terms of the currency.